So now that we've talked about the structure and functionality and the key methods in Java CyclicBarrier, we're going to take a look at a fairly sophisticated example. And this example is actually a variant of the example we saw with the Java countdown latch videos, where we were using this thing called the GCD application as a case study. This particular example, of course, is going to use CyclicBarrier objects to coordinate the concurrent benchmarking of four greatest common divisor, or GCD, algorithms. And if you go here and you download this code and you run the example, you'll see what it does. It has four different versions. It has a GCD iterative Euclid algorithm implementation. It has a GCD recursive Euclid algorithm implementation. It uses the GCD method that's built into the integer class in Java, and it uses some wacky one that involves binary operations, which is completely insane. And it basically times them to see how long they take to run, and it visualizes. It's actually kind of fun. And the results are somewhat surprising, perhaps, if you don't know about how these things are implemented. So I won't run the application, but you're welcome to download it and play with it. It's really fun. And you probably know what a GCD is by now. It computes the largest positive integer that's a divisor of two numbers. So the greatest common divisor of 80 and 120 is 40. There are four algorithms tested. There's the GCD method defined by the big integer class. There's an iterative Euclid algorithm. There's a recursive Euclid algorithm. And there's a complex GCD algorithm that uses binary arithmetic. You can read about that algorithm here. Oddly enough, at least in Java, it doesn't really give you much of a win. Maybe if you wrote this in assembly code, it would give you a win, but it's not really a big win in Java for various reasons. The details of these algorithms aren't really important for our discussion. We're really here to talk about the use of barrier synchronizers. In this particular case, cyclic barriers. That's what's important here. So here is the test program. You can see that it's a JUnit test because we have the test annotation up here. And you can find the source code in this link. And here's the entry point into this unit test. It's called Test GCD CyclicBarrier Tester. So that should hopefully give you an idea of what it does. So there's a few things here we're not going to spend a lot of time on. There's a factor method called make GCD tuples, which initializes all the GCD algorithms, and it sticks them in a list. So we have a list of GCD tuples, and that contains all the information needed to run each of the algorithms. We then go ahead and create the entry barrier. Now, the entry barrier, the purpose of the entry barrier, as usual, is to wait for all the threads to be started before it lets any of them go. And that's the idea. We want to kind of do a apples-to-apples comparison of their performance. So it wouldn't make any sense to start them in some order where the first one that gets started gets to run while the others are still being started. That wouldn't be fair, because that particular thread, whoever starts first, is most likely to get an advantage, all other things being equal. So what we're going to do is we're going to make ourselves a new cyclic barrier, which keeps track of the number of tests. There are four, because there's four algorithms, plus one. And the plus one is because we want to add another party, another thread, for the thread that is initializing all these tests and actually putting everything in motion. So there's 5 threads here, 4 of which are running the algorithms. We also provide a barrier action that's going to allocate and then reallocate each cycle the input that's used to process stuff. So you can see here that we're going to initialize the input for the number of iterations, and this will basically reinitialize all the random generated test values. So we're going to reinitialize or reallocate those each time. Now we also create ourselves an exit barrier. And the exit barrier is going to be used to wait for all the processing to be done. So the entry barrier waits for all the threads to be ready to go before it lets anyone start to process. And then the exit barrier is used to wait till all the threads are done before we wrap up the test, or wrap up the cycle in this case. And as before, we have the number of algorithms plus 1. That's the thread that's going to be running this loop. So now we go through a loop, and basically we're going to have S cycles iterations. So let's say it's 10 or whatever, or 5. So we're going to run this thing for a total of whatever S cycles is set to. That's just a static value. Let's say it's 10 for sake of argument. And then what we do here is we're going to go through each of the tests, and for each test, for each algorithm, we're going to make ourselves a new thread, and we're going to start that new thread. But we're going to pass in the entry barrier and the exit barrier to the runnable that's going to do the processing. And that, of course, is going to be used by that runnable in order to make sure that all the threads start at the same time and all the threads exit at the same time. And we'll see how that code works when we walk through GCD CyclicBarrier Worker in just a moment. So that's going to basically be an implementation of runnable. That's so we can pass it as a parameter to the thread constructor. And the key thing to note is we pass in the entry barrier and the exit barrier. We'll see that in a second. Now, we print out starting tests. That's just a diagnostic, but the tests aren't running yet. They're getting ready to run. And it's not until all the worker threads are these threads that are spawned here, and the calling thread, the one that's doing all the initialization, it's not until they all call await that they can start to run. So again, there are 5 threads, let's say, and when the 5th thread calls await, whichever that thread might be, it might be this thread, it might be one of the other threads that started, whichever one ends up being the last one to be calling await, at that point, then everything can start to execute. And this fixes a limitation with countdown latch that we had seen earlier, where countdown latch had this problem in that it wouldn't prevent things from starting to run. It would make them wait till everything was done, but it wouldn't prevent them from starting to run. So that fixes a problem with countdown latch. So now they're all off doing their thing. This thread here, the main thread or the calling thread calls waiting for results, and it's going to just basically block. And then the initialization thread calls await, and that will block until all of the threads that are running the algorithms have finished as well. And we'll see how that works in a second. So they all have to call await, and when they all are done calling await, then we can say all tests done for this cycle. And we loop back around again and start over at the next iteration, assuming we haven't finished the iterations in our cycles. So what's nice about this is after await returns for a cyclic barrier, be it an entry barrier or an exit barrier, the barrier is automatically reset and can then be reused without needing to create a new cyclic barrier instance. And that's really how it differs from countdown latch, where it was, you couldn't reset it. Excuse me. So now that we've kind of seen the overall driver program here that creates the entry barrier and the exit barrier and then creates a GCD CyclicBarrier worker, let's take a look at the GCD CyclicBarrier worker. That's the thing that's really doing the processing here. It's running the algorithm. So as you might imagine, GCD CyclicBarrier worker implements runnable. So that's how we can pass it to a thread constructor. And it's got a bunch of fields. It keeps track of the entry barrier and the exit barrier. Those are set in the constructor. And then here's the run hook method. That, of course, is what gets invoked after the thread is started. And you can see here that each of these threads, remember there's going to be as many of these calls to run as there are GCD algorithms to be tested. They're all going to call await, and they're all going to block there until everybody's await has been called, at which point they can proceed. And that, again, fixes that earlier limitation with countdown latch that we saw in our previous lesson on countdown latch and the example there. So after everybody calls await, then they return. The test then runs, and whatever implementation we've got, it'll do that implementation of the GCD algorithm. We don't really care about that implementation. All we care about is the structure and the barriers. And then when a given GCD algorithm is done, it calls exit barrier await, and that waits until all the threads are done before it'll return from await. So they all block here, getting ready to start. They all start at the same time. They all run at the same time. and then they all wait until they're finished, and then they go on to the next cycle. Yes, sir. Well, okay. So the question I think here is, there's a bunch of threads running around. The bulk of them are doing the GCD algorithm, and then we have kind of this orchestration thread, which is this guy. I called it the initialization thread, but it's really the one that sets the wheels in motion, if you will. And so I think maybe the question is, what's going on here? If you look, we await, and then we await again. And so what we're doing here, this is basically this is being used to make sure that this call to await, in conjunction with all of these calls to await, are just making sure that no thread continues until they're all ready to go. So the main point, the really important point, is that the GCD algorithm threads can't start running until they're all ready to go, until they're all launched and started. They have all their state, they have the runtime stack, and they can all start at the same time. And if you think about what's going on under the hood, we've got a multi-core processor, and so literally those GCD algorithms will in fact be running in parallel, which is pretty cool. The use of await here is just to have this controlling thread, because we want to start them all at the same time, we want to wait for them all to finish at the same time, and then we want to loop back around again and do it again. So this guy is really just kind of the master of ceremonies, making sure that everybody starts at the same time, waits for them all to finish, goes to the next iteration, it starts over again. So this guy that's why this thread has a wait, and that's why we have an exit barrier and an entry barrier. If we didn't have these things, well, especially if we didn't have an exit barrier, then the cycles would be all, intermixed and interleaved, and it would be confusing. The output wouldn't be sort of chunked by cycle. That's why we have the call to await for the entry barrier to start everything up, and a call to the exit barrier to wait for them all to finish. And then we go to the next cycle. Does that help? Okay, super. Yeah, that's a great question. So the exit barrier here just waits until all the threads are done before it returns, and of course each thread waits for all the other threads to finish before they can all return at the same time. So that's the end of our example application of Java CyclicBarrier. I think you'll probably agree that it's pretty cool if you have problems that need cyclic execution with a fixed number of threads/parties. So CyclicBarrier works very well for group processing, where the number of elements, number of threads or parties in that group are known in advance and don't change.